Okay, sorry, the video was going too long now and I had to stop it. Where were we up to? We're up to logging both sides. Why are we logging both sides? Because to find this point of inflection, we need to know the t-value, and the t-value is locked up as the power of E. Right? So, like He-Man when he held aloft his magical sword and found he had the power, I would need to log both sides to get that power. Right? So log is the inverse. This is natural log. The natural log is the inverse of the E function, right? And I will just be left with bt. Right? And over here, I've got log A, and this is going to lead me to a place where we now know that t is log of A, the natural log of A divided by B. We're running out of room, so let's just make a note of that. And we'll keep going, because the question in the book says we don't just want the x part, the t. We also want to show what the y value is, right? Or what the function will spit out when I insert t equal to log A and B. So we need to find this point of inflection in its entirety, not just the x value. So I'm going to have to sub this x value back into the original function. It's going to be log A, B, right? And that will equal c divided by 1 plus A, and I've got A to the minus B times log small writing A divide B. Right? Just for a minute, just focus in on this bit here. What's going on there? We've got a minus B times log A all divided by B, right? So what happens? B divided B is just 1. So this just equals minus log of A. And using one of my log laws, I know that minus 1, or minus whatever number's out in front of the log, times the log is the same as log of A to the power of minus 1. Right? This is the log law that says these m's and n's. Right? Now don't worry too much about this at the moment, because we're going to do a topic on logs and brush up on these log laws. And it won't be tested in your next test. If it is, I'll give you a bit of a heads up. Right? So now I need to remember that all of that ended up being ln of A to the minus 1. So this here is C ln plus A E to the power of ln A to the minus 1. Right? Remember, log is the inverse function of E, so that therefore follows that. Therefore, f of t at this point equals c on 1 plus a, and this is just going to end up being a to the minus 1. So what does this all reduce to? This is a to the power of 1. We've got the same base. We've got a multiplication. So what do we do with the powers? We add the powers. Right? So we're going to do 1 plus minus 1. That equals 0. This whole thing will just become 1. Because we'll have a to the power of 0, and anything to the power of 0 equals 1. So there's my y component. Right? So when t equals, maybe if I write this as a coordinate, or if I just say 1 f of t equals c2. Now just to finish off, let's put all this information on a graph. I did show you a picture in the first video. Let's do it again. Let's start by drawing perfectly straight lines for the axis. Function here. You could write y there if you like, it doesn't matter. You could say y equals f of t. And that's fine. If you remember, where did we start? We found the y-intercept. The y-intercept is where t equals 0, so we're just left with c 1 plus a. Right? Then we looked at the horizontal asymptote. Right? That's y equals c, or the f of t equals c. Okay. And we've got a point of inflection. We've got logistic curve, concave up and concave down. And this point here is ln a b c on 2. Okay, so I think that question's pretty much complete now. We might want to add that the second derivative will be positive in this region here where the gradients are increasing, and the second derivative will be negative in this region here where the gradients are decreasing. Okay? So thank you for watching. Hopefully that was useful. I think if you can do that question in its entirety, it's pretty good practice in doing these derivatives when you've got a's, b's and c's. And it's worth doing this question because the function itself is really quite interesting. Like I said, it's sometimes called the S-shaped curve, and it's used to model population growths. Thank you.